Greetings and welcome. In this video session, we are going to see a numerical on a Bootstrap cooling system, which is used in a aircraft refrigeration system. We have seen in a theory that a Bootstrap system is a advanced cycle of a simple air cooling system. In a simple air cooling system, one compressor and one heat exchanger is used. In a Bootstrap cooling system, there are two compressors. First compressor is a main compressor, we call it as main compressor, and second compressor is called as auxiliary compressor. And along with that, here are two heat exchangers. After each compressor, there is a heat exchanger. First heat exchanger is called as air cooler, and second heat exchanger is called as after cooler. Now we will solve this numerical. So before that, we will first of all read the statement, and after that we will fetch the data. So here a Bootstrap cooling system of 10 TR is used. 10 TR is a capacity cooling load. The ambient air temperature and pressure, these conditions are given 15 degrees Celsius and 0.85 bar. The pressure of air increases to 1 bar. This is what ramming process. So ramming pressure is increased to 1 bar, and it is of type isentropic is mentioned. The pressure of air discharged from the main compressor, means after main compressor point number 3, that is given of 3.5 bar. Discharge pressure of air from auxiliary compressor, means second compressor, this will be point number 5 in a TS diagram, that is of 4.25 bar. Isentropic efficiency of each compressor is 90%, while that of turbine is 85%. Effectiveness of both heat exchangers are 0.7. Cabin is to be maintained at 22 degrees Celsius. This is a cabin condition. Last point in the TS diagram, we will see that point number 8. And the pressure in the cabin is 0.9 bar. Here we are given constant values, means the value of specific heat of air, that is 1.005 kilojoule per kg Kelvin. Adiabatic index is given 1.4. And we have to determine the three things here: mass of air, power of the system, and COP of the system. So let us first of all enlisting all these values. We will see. We have to enlist the values now. So here, as per the given data, we have written values: cooling load, TR to kilowatt conversion, that already we know. So here we can see 35.17 kilowatt. Condition of air at the entry of the diffuser, that is before ramming, P1 and T1. Pressure and temperature. Here value of temperature T1 we have to convert into Kelvin, say in a Kelvin. After ram, value of pressure P2, that is point P2, and isentropic, that is also written. Here after main compressor P3 pressure. Now here after P3, the line is a isobaric line. After the main compressor, that air goes through the cooler, we call it as air cooler, heat exchanger for the heat removal purpose. So here the fourth point on that line, isobaric line, so that is P4. That is why P3 and P4 both are identical or same. After auxiliary or secondary compressor, here the pressure is given, and here also after second compressor there is a second heat exchanger. So that second heat exchanger, through that process is of heat rejection, that is 5 to 6 process. So that is why isobaric process means P5 and P6. These are same. At the end, when the air is reaching to the cabin, their condition of a pressure, that is P7 to P8 is given, and temperature is given. Here are the efficiency of both compressors, turbine and heat exchangers, that is effectiveness values. Now what is asked to us, that is first of all mass flow rate, means m dot a in a kg per second, this we have to find. Then power means net work, that comes in kilowatt, and third is a performance parameter, coefficient of performance. So these three we have to find. So for this, now first of all we have to draw the TS diagram, because TS diagram helps us to write the formulas for different processes from 1 to 8. So let us draw first of all TS diagram. So we will start with the TS diagram. So here in the TS diagram we see the vertical axis, that is temperature, and horizontal axis, that is entropy. Here we have these different pressure lines, isobaric or constant pressure lines. We will start first from the ambient pressure line. So this is ambient air, ambient air. So here are the condition is P1. So from point number 1, if you take, and it is isentropic process, so that is why ramming process, that is 1 to 2. So from 2, this will be ramming operation. So during this journey, pressure of the air increases from 1 to 2. Here the values we will mention. P1, entering air, is at 0.85 bar. Here after ramming, this is a pressure P2. So P2 value is given, that is 1 bar. Then from 2 to 3, that is a main compression. Here the compression is shown by the two paths. One is a adiabatic process, isentropic process, and this is an actual process. So this 2 to 3 dash is ideal process, and 3 is a actual process. This is a main compressor. In main compressor, this process happens in main compressor. So here the pressure P3, after the main compressor P3 pressure, that is 3.5 bar. Now onwards, this 3 means after the exit of compressor, then comes heat exchanger. So for the heat exchanger, it is a heat removal process. So for that, we can take this 3 to 4 process, that is heat removal. So that is why here this line is coming back. Here temperature is reduced. So this point number 4, that point number 4 is the end of the first heat exchanger. So that is why this point 4 is lying on the isobaric line, this 3. So that is why the pressure P3 and P4, so both are same. So that is 3.5 bar. So this is what constant pressure process. Then here secondary compression, second compressor. In that, here again this vertical line we can show by the this is a second compression process. So here again are the two ways, actual path and ideal path. 4 to 5 is actual and 4 to 5 dash is a ideal in a secondary compressor. So here after this pressure P5, that is here 4.25 bar. After the secondary compression, then again there is a what? Cooler, after cooler. We call it as after cooler. So in the after cooler, if we show, this is a process of cooling of air in after cooler. This process after cooler up to 0.6. This is also constant pressure process. That is why point number 5 and point number 6, P5, P6, both pressures are same. Then here turbine, this air goes in the turbine where the isentropic expansion of the air that is taking place. So this isentropic expansion of the air, and this is actual expansion of the air. So here 7 dash, 6 to 7 dash is a ideal, and 6 to 7 is a actual expansion of the air. And then this air goes to the cabin. So this air goes to the cabin. So here is a point number 8. So this is a journey of the air from the turbine to the cabin. So during this journey here, heat is captured or received by the air, which is a heat load. That heat load from the cabin, that heat load is absorbed by this cold air. This load we call it as a cooling load. Okay, so in this way we have shown all the now points. Here again we can say that P7 and P8 are same because isobaric process. So in this diagram we can show, or we can see all the points. Point number 1, its pressure and temperature value is given. T1 temperature value, here we can write T1, that is 15 degree Celsius, means 298 Kelvin. So here condition of air at the entry, this we know. So from this we come to know that here unknowns are point number 2, temperature. Here temperature point number 3, 3 dash. All the temperatures onwards, all are unknown. Only temperature point 8 is known, that is given 22 degree Celsius. So to find this temperature, that what we use in a theory that we have seen, we have for every process 2 formulas. Wherever the compression process, there one formula comes for the temperature ratio, pressure ratio relation, and second formula comes, that is efficiency. So here we will have 2 formulas for this 1 to 2 process. Then for main compressor 2 formulae. After that here 2 formulae will be for the second compressor. For the turbine also 2 formulas. It's about 8 formulas we will use. And also in between, for the process of heat exchanger, we have to use formula of heat exchanger for the air cooler and for the after cooler. Means here these are the 2 formulas. Means about 10 formulas we have to use to find all the unknown temperatures which are required to find the 3 whatever unknowns, that is mass flow rate, power and CO. So let us start from the ramming process. So for the ramming process, so in a ramming process, process 1 to 2, that is a identical process, isentropic process. So for isentropic process, we have to write relation for temperature and pressure, that is T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma. Here this formula we have to write in the terms of T2 because T2 is unknown. All remaining are known values. So T1 temperature, that we have written here in a Kelvin, and pressure values. And already we have seen in last video sessions in a simple cooling cycle numerical that gamma minus 1 upon gamma. This calculation that comes 0.2857, that we take here. So by doing this calculation, we find the temperature T2, that is a actual RAM, or we can say diffuser, the process which occurs, that is a actual diffuser exit. After the diffuser, this is a temperature, that what we get. Now the process 2 to 3, that is in a main compressor, compressor number 1, that is called as main compressor. For this process, again the same way, this is a temperature relation formula between 2 and 3. T3 dash divided by T2 is equal to P3 by P2 raised to gamma minus 1 upon gamma. This is the formula. This is the arrangement of the formula in order to find the T3 dash. Putting the value of T2 calculated in last step. P3 and P2 are given. 3.5 is a P3 means after first compressor, and P2 is after ramming. This is a calculation of this part. So by doing the calculation, we get T3 dash. Now this T3 dash we can use to find the value of T3. Here are two formulas. One is a temperature relation and another is a compressor efficiency formula. So compressor efficiency formula is a what? Here temperature rise for the ideal process, that is T3 dash minus T2 divided by temperature rise for actual process. So in this case, as the compressor efficiency is given first for the compressor, both compressor same efficiency 90%, means 0.9 we take. Here T3 dash 431.51 and T2 value of T2 that already we calculated, that is 301.68 divided by T3 minus T2 value. By doing this calculation, we get the value of T3 445.93 Kelvin. This is compressor 1 or main compressor exit, main compressor actual exit temperature, actual this is a 0.3. This is a main compressor, already written here. So for point number 3, this is the actual temperature that we have got. Now the further process, that is we will see. Next to compressor 1, the process is cooling process that take place in a air cooler, heat exchanger number 1, process 3 to 4. So here effectiveness means performance of the heat exchanger number 1 is how to write. This is a cooling process. During this, temperature T3 is reducing to point number 4. So this is the outcome, T3 minus T4 divided by this temperature 3 is raised or increased because of compressor 1 up to point number 3 from point number 2. So T3 minus T2 is a denominator. So this is what output and this is what input. Effectiveness formula, here effectiveness is given 0.7. T3 value is a calculated, T4 is unknown. T3 and T2 both are calculated. By putting this, we find the value of 4. This 4 value is what? Exit of heat exchanger 1, or it is an entry to the compressor, that is the next compressor. So this is what? Entry temperature of second compressor, auxiliary. So further process 4, 5 that is taking place in an auxiliary compressor. So here in a compressor we use again two formulas. First formula for the pressure, temperature pressure relation, 4 to 5 dash ideal process, actual process. So this is a temperature ratio, pressure ratio raised to gamma minus 1 upon gamma. Here unknown is a T5 dash. So we have arranged formula in the form of T5 dash. T4 we calculated, T5 and T4 are given. 3.5 bar is a pressure. Point number 4 means after the discharge pressure after the main compressor. That is a entry pressure for the secondary compressor. And this is a exit pressure of the second compressor, auxiliary compressor. So by putting the value of this P5 by P4 here and this calculation of gamma minus 1 upon gamma we have put here, calculation we did. So we find the value of T5 dash, point number 5 dash. 5 dash is a ideal point of the compressor second exit. So this is a temperature. Now to find the actual temperature, exit temperature of the second compressor, we have to use formula of efficiency for the second compressor. For the second compressor efficiency concept is what? Temperature rise, ideal temperature rise divided by actual temperature rise. So this is ideal temperature rise, T5 dash minus T4, and actual temperature rise, T5 minus T4. Here unknown is T5. T4 value we calculated, we put here. T5 dash also we calculated by putting the value all here. Here compressor efficiency for the both is given 90%, so 0.9 is a efficiency. So we find the value of T5, that is second auxiliary compressor actual exit temperature, that we obtain, that is 366.80. The further process is a cooling process which occurs in a second heat exchanger, 5 to 6 process. Here the unknown we have to find, that is 6 point unknown. To find this we can use the formula of effectiveness of heat exchanger 2. So here the case is what? This is a 5 to 6 heat removal process, 5 to 6 heat removal process. During this heat is rejected which is being absorbed by the air during the compression processes. So here T5 minus T6, this is the output, and this heat is because of the compressor, both compressions. Compression 1 is here and this is second compression. So from point number 2 to 5, the temperature of air is increased due to compression 1 and 2. So that is why difference between this point number 5 at the end of second compression and point number 2, that is a entry of first compression. So T5 minus T2, this will be what the denominator. So here the value of effectiveness for the both heat exchanger is given 0.7. Other values T5 is calculated, T2 is calculated. So all the calculated values we have put, and getting the calculation we find this value T6. So this point number 6, that is what exit of the heat exchanger, or we can say entry to the turbine. This is exit of second heat exchanger, means after cooler. Name of that in theory we have seen, after cooler, and it is also entry of turbine, because the next process will be 6 to 7 process that will happen here, that is in a turbine. So now we will go to the process, turbine process. So here we have seen this is a second heat exchanger process. So second heat exchanger process that is occurring in the point number 5 to 6. Here unknown is a 6 point. That is why we have to use formula for the heat exchanger of the heat exchanger effectiveness. Effectiveness is what? Here the after cooler, this heat exchanger 2 is removing heat from the air. Thus, temperature of air from point number 5 is reducing to point number 6. So T5 minus T6. This is the output of the heat exchanger. This heat is obtained or heat gain to the system from what? Because of what? Because of compressions. This is a compression number 1 and this is compression number 2. So from point number 2 to point number 5, the temperature is increased. So this is the difference of temperature of air, that is addition of heat, T5 minus T2. So that is why we take this at the denominator. In this formula, effectiveness is given 0.7 and temperature of 5 point and 2 point are calculated in previous steps. So by putting the values and doing the calculation, we find the temperature, that is exit of second heat exchanger, or we can say this is the entry of turbine. So this actual temperature, this is what actual temperature what we get from this calculation. So here the next process is a process 6 to 7 that occurs in turbine expansion process from 0.5, 0.6 to 7 ideal process, and this is actual process. Here we use two formulas. First, temperature ratio formula. So T7 dash divided by here is a T7, that is ideal process, and this is actual. Ideal point, actual point. So T7 dash divided by T6, this is a temperature ratio for the ideal process, is equal to pressure ratio P7 divided by P6. We have to find T7 dash, that is why we arrange this formula in this way. T6 we calculated in last step, P7 and P6 pressures 0.9 and 4.25 bar, and this calculation is we have put here. So doing the calculation, we find the temperature T7 dash this. Now this temperature we use we put in the formula, that's its second formula for the efficiency of the turbine. So efficiency formula is actual temperature drop of the turbine, means T6 minus T7 divided by ideal temperature drop. This formula we have studied in a theory. This small difference divided by large difference. So here again turbine efficiency is 85% given, so 0.85, and the values which are here 6 and 7 dash, these are already calculated. So we put the value of T7 dash over here. T6 value is already calculated in last step. Turbine efficiency is given 0.85. So putting all these values, unknown value T7 we get. This is what point number 7, that is on the actual line, means it is actual exit temperature of the turbine. So in this way, by using the heat transfer and thermodynamics concepts, for air standard cycle and TS diagram, we have calculated all the temperatures from point number 2 to point number 7. All the temperatures we calculated. Now the point comes, that is calculation of 3, that what is expected in the numerical: mass, flow rate, power, and the third COP. So for that we have to write the formula one by one, and putting the values we can calculate. So we will write the formula for the mass flow rate first. So for mass flow rate, we know the cooling load formula. So this is a cooling load formula. Cooling load formula, how to write? So we can see, already we have discussed about it, but again here we can take the help of TS diagram. Here you can see this is a exit point of the turbine, point number 7. So point number 7, air is passing to the cabin. So during this 7 to 8, this is the cooling load. During this process, there is a load from the cabin that is added to the air or on the system. That load comes on the system, and that is why here we take the difference between point number 7 and 8 in the formula. So here the formula is MCP delta T means T8 minus T7. Q dot L here 10 TR is a given, conversion into kilowatt, that is 35.17 kilowatt. M dot A is unknown. CPA value of the air that is given to us, and value of temperatures are one is calculated, and this cabin temperature is given 22 degrees Celsius in absolute 295. So by doing the calculation, we find the mass flow rate of air, that is the mass of air circulated throughout the system in kg per second. This is the value. This is what answer number 1. Now the next calculation is what of power. So for the power, we second calculation, power required to drive the system. Now here compressor 1, that is what network. Now network, how to calculate? Here we take two compressions, two works. First is of RAM and second is of compressor 1. This formula we take into consideration. Now why not second compressor work? Because here in a second compressor, that second compressor is connected to the turbine. Means second compressor is, this is a second compressor that is driven by the power of turbine. So turbine power is utilized to drive the compressor 2. So that is why here power of the compressor 2, that part is not taken into consideration in the calculation of net power. So here we have to find WR dot means for RAM and WC1 means for compressor 1. So for that formulas are MCP and corresponding temperature difference. Ramming process occurs between point number 2 and 1. So that is why here the formula is T2 minus T1, and compression 1 that take place between point number 2 and 3. So here T3 minus T2. So now we will put the values. So here W dot R RAM work formula, in that we put the value of mass flow rate calculated, CP value for the air, and T2 minus T1, these temperatures. This consumption, work consumption for the RAM comes 6.7 kilowatt. Similarly, by putting the values for compressor 1 in a formula, we find the consumption 70.70 kilowatt. Now the net consumption is what sum of these two values, that comes 77.40 kilowatt. So this is what power to drive the or to run system. This is what your answer, second answer. Now third answer is COP. COP is ratio of output, that is Q dot L divided by input, that is net work. So here Q dot L, that is a 10 TR in a kilowatt, and net work what we calculated in a kilowatt. By putting these values over here, we find the COP 0.45. This is a COP, which is answer third in the statement. So in this way, we calculated this, all the values which are in the numerical. If you see from the start, here you can see this is a input data given, and then one by one, here first of all we drawn the diagram of temperature entropy TS diagram, because it is needful to write the formulas. So by writing the formulas and following all the processes, all the processes we followed, and after following all the processes we obtain the temperatures, and at the end, by finding all the temperatures, then we find the mass flow rate, then we find the power, and finally COP of the system. So this was the numerical treatment of the Bootstrap air cooling system, which is used in an aeroplane for the air cooling purpose.